Let's talk about the periodic table. You've seen it a million times, right? But have you ever looked closely and wondered, what is up with all those weird decimal numbers? I mean, protons and neutrons are whole things, so why isn't the atomic mass a nice round number? Well, that little puzzle is exactly what we're going to solve today. The answer's been hiding in plain sight this whole time.
So yeah, this is our big question. It seems so simple, but the answer peels back a fascinating layer about how elements actually exist out in the wild. Turns out, that number you see on the chart isn't the mass of one single typical atom. Oh no, it's something way more interesting than that. To get to the bottom of this, let's zoom in on one element. How about magnesium? The periodic table says its atomic mass is 24.305. But hold on, mass comes from protons and neutrons, right? And you can't have 0.305 of a neutron. So what gives? Why isn't it just 24 or 25 or 26? To figure that out, we got to go back to basics and ask what makes an atom? Well, that specific atom.
All right, so to crack this code, we first need to understand what part of an atom is completely non-negotiable. What's the one rule that absolutely defines what an element is?
And the answer is, it's all about the protons. The atomic number, which is just the count of protons in the nucleus, is like an element's unchangeable fingerprint. It's the one thing that is set in stone. Every single magnesium atom in the entire universe has exactly 12 protons, no exceptions.
And this is a hard and fast rule. 12 protons means you're looking at magnesium. If it suddenly had 13 protons, it wouldn't be some weird version of magnesium anymore. It would literally be a different element, aluminum, full stop. So if the protons are locked in, what can change? Well, that leads us right to our first big clue. This brings us to where things get really interesting. See, elements don't usually exist as just one single type of atom. They often come as a whole family of different versions. These different versions are called isotopes. You can think of them like siblings. They're all part of the same magnesium family because they have the same number of protons, but they all weigh a little bit different because they're carrying a different number of neutrons.
So let's bring this back to our magnesium example. In nature, we find 3 stable isotopes. Now look at this table. Notice they all have 12 protons. That's what makes them magnesium. But check out the neutrons. Magnesium-24 has 12. Magnesium-25 has 13, and magnesium-26 has 14. So their mass changes, but their chemical identity as magnesium stays the same.
But here's the real kicker, the piece of the puzzle that changes everything. These isotopes aren't found in equal amounts, not even close. If you can scoop up a random sample of magnesium atoms from anywhere on Earth, you'd find that almost 79% of them are the lighter magnesium-24 version. This idea of natural abundance is the final piece we need.
Okay, let's pause for a second. We've got our 2 big clues. Elements have different versions called isotopes, and some of those versions are way more common than others. That's it. We now have everything we need to finally solve the mystery of that decimal point.
So that number on the periodic table, it's a weighted average. It's not a simple average where you just add 24, 25, and 26 and divide by 3. No way. A weighted average gives more importance, more, well, weight, to the isotope that's the most common. Since magnesium-24 is the superstar here, the final average is going to be pulled much, much closer to 24 than to 25 or 26.
And believe it or not, the math is pretty straightforward. Here's how it works. First, you just take the percentage for each isotope and turn it into a decimal. So 78.99% becomes 0.7899. Easy enough. Then, you multiply that decimal by the super-specific mass of that isotope. And for the last step, you just add up all those results you got.
So let's plug in the real numbers. We take the abundance of magnesium-24, that 0.7899, and multiply it by its exact mass. Then we do the same for the 10% for magnesium-25, and finally the 11% for magnesium-26. So what happens when we add all 3 of those pieces together?
Boom! 24.305 atomic mass units. Look at that. It's the exact number we saw on the periodic table. So, mystery solved. That decimal isn't the mass of a single atom. It's the average mass of all the magnesium atoms on Earth, perfectly balanced by how common each version is.
Okay, so we've got the neutron situation all sorted out. But what about that other particle flying around, the electron? What happens when its number changes?
Well, when an atom gains or loses electrons, it becomes what we call an ion. Electrons have a negative charge, right? So if an atom loses one, it becomes positive. If it gains one, it becomes negative. The really important thing here is that this only changes the atom's charge, not its identity as magnesium. And since electrons are incredibly tiny, it barely affects the mass at all.
Let's just put this side by side to make it super clear. You change the number of neutrons, you get an isotope, and that affects the atom's mass. You change the number of electrons, you get an ion, and that affects its electrical charge. But the protons, you don't touch the protons because that changes the element completely.
All right, let's zoom back out and recap what we've really figured out about that funny little number on the periodic table.
So here's the bottom line. An element's ID card is its proton number. That's locked in. Vary the neutrons, you get an isotope. Vary the electrons, you get an ion. And that decimal on the periodic table is just a clever weighted average that accounts for all the isotopes out there, which leads to this kind of mind-bending thought. That average magnesium atom, the one with a mass of 24.305, it doesn't actually exist. You'll never find one. You'll only ever find the ones with a mass of about 24, 25, or 26.
And that leaves us with a much bigger question to chew on, doesn't it? The atomic mass is a super useful simplification, an average that lets us do a ton of amazing chemistry. But as we just saw, it hides all this rich variety and complexity underneath. It really makes you wonder, what other averages do we use every single day that might be hiding a much deeper and way more interesting story?